in this topic? Nearly. Not everything. I can make it happen, but it's going to be nearly it. Now, I know you guys said, oh God, but think about it. We are what? A week and a half away from exams, is that right? What better time to wrap it all up? You know what I'm saying? This is phenomenal. I don't know how many courses you get to do this in, where you just get to tie everything together at the end, but this is phenomenal. Good. All right. I don't even know what those questions are. I only have a small amount of material to teach you yet. That probably is not going to happen until very early of next week. Okay? It's only going to be like a day, possibly a day and a half. We're done learning. Now we're just tying things together. There is a concept that I'm going to have to review with you early on here. In fact, I'm going to go ahead and use question number 11. We're not going to walk through all 4 of those, 11 through 14, because I don't think we're going to need to. But I'm going to pick the ones that I believe are going to be enough to get us started. Okay, let's look at number 11. You don't have to write, you probably better write this stuff down. So the equation that we have, I'm going to go through the format that is going to be helpful here. First of all, what type of reaction does this appear to be? Of all the ones we learned way back after Christmas, I believe. What's that? It looks like a double replacement. In fact, it acts like it looks like one, breathes like one, smells like one, tastes like one. I'm probably not going to say taste, okay? However, it's a special case of double replacement reaction. Does anyone remember what types of substances are currently involved? What is H2SO4? It's an acid. What is any ionic compound that has hydroxide in it, such as sodium hydroxide? It's called a base. Therefore, this is an acid-base neutralization. Okay? I'm not going to make you dig this out, but if you care to at some point in time dig back into your little chemical equation packet, you remember you guys had a packet for that? This was the last one we covered. Acid-base neutralization. To make sure everyone is clearly on the same page, how do you recognize an acid-base neutralization? Well, obviously, one of the substances is going to have to be an acid. The other substance is going to have to be a base of some type. Currently, for the next week, you are going to recognize a base because it's going to have hydroxide. It's going to have hydroxide. Is everyone hunky-dory with this? Okay. This is the hydroxide ion. We are going to consider substances that have hydroxide ion as bases. This is, as you all know, an acid because its formula starts with hydrogen. So, therefore, this is an acid-base neutralization. Does anyone recall the products of any acid-base neutralization? Bless you. Twice. One's all the same. One's always the same. He's allergic to acid-base neutralizations, by the way. Is that right? Yes. Water. Okay, because what happens is, if you think about this, the hydroxide will react with the hydrogen to form water. So one of the products is water. And then, if you recall, the other product is a salt of some sort, okay? Remember, salts are ionic compounds. This particular salt is going to be what? What's left? Sodium sulfate. Does anyone remember this charge on the sodium ion? 1 plus. Does anyone remember the charge on the sulfate ion? 2 negative. Good. Is this the correct formula? NaSO4? No, it's Na2. We have to cross over, bring the 2 over here, okay? And that's going to remain in solution. Okay, so now we have the products. What do we do next? What do we check for? Once we've written correct products, go ahead. Balancing, is this balanced?
No.
Okay, anyone have any thoughts? 2, 1, 2, 1. Anyone concur before I write these up there? That look good? Okay, we'll go with it. All right, so there we go. There's the balanced reaction for the acid-base neutralization. Now, I know that it's already currently on your sheets, right? I get that. But I'm telling you right now, as we start working through these things, they're not always going to be there. So you have to figure it out. So I walk through it. Just ring a bell. This is nothing new. This is nothing new. We did this back in January. Okay? Next, we're given some information. I believe that we have 0.5 molar sodium hydroxide. And we have 40 milliliters of 0.5 molar sulfuric acid. I am asking you what volume of sodium hydroxide is going to be required to completely neutralize the acid. So we've got this acid, we've got 40 milliliters of acid sitting around. So I've got this container. So let's say I have this container, which by the way, you guys know this as a, what particular type of flask? Erlenmeyer flask. Let's say we have 40 milliliters of some sulfuric acid in here, and it ends up being 0.5 molar. Mix it up back there, 0.5 molar. I want to neutralize that. What does that mean? To neutralize? Add some base, okay? To neutralize means to add some base. The question is, how much of that base am I going to need that is 0.5 molar also to completely neutralize this? Does everyone see the question that I'm asking? Does everyone understand what I'm trying to ask? Now, here's the thing. How do we go from an amount of one thing that we know to an amount of a different thing that we don't know? What's that called? Stoichiometry. In order to do stoichiometry, you have to use a mole ratio. In order to use a mole ratio, you have to be in moles. Right? Does anyone now do we have enough information here to get to moles? Well, what is molarity? Yeah. Molarity is moles over volume of solution. Moles of solute over volume of solution. Do we know the molarity of the sulfuric? Yes. Do we know the volume of the sulfuric? Yes. Therefore, moles equals what? Molarity times the volume. Plug and chug. We get 0.500 molar times. Now, this is in milliliters. When we're using this equation, the volume has to be in liters. So, yep, 3 places, 0.0400 liters. Okay? What's 5 times 4? 20, but we're going to have to move the decimal point a couple places, right? Should be 0.02, is that what you did? Now, that's how many moles of sulfuric acid we have. Have you guys done calculations like this before? The answer is yes. Okay? Now, as someone said earlier though, that's the moles of sulfuric. We need to ultimately get to moles of sodium hydroxide, because if I know the moles of sodium hydroxide and I know the volume, or sorry about that, the molarity of sodium hydroxide, I can calculate what? The volume of sodium hydroxide, just by rearranging this equation. So, we're doing our stoichiometry now. Whoa, that's not correct. It's 2 moles of sodium hydroxide, would you guys agree? For every 1 mole of sulfuric. So we're essentially going to double that, so 0.0400 moles of sodium hydroxide. And now I come over here and say, well, hey, I know the moles of sodium hydroxide. I know the molarity of sodium hydroxide. I can rearrange that equation and solve for the volume. Volume equals, would anyone like to throw that out there for me real quick? Moles over molarity. And what's the molarity? 0.5? So times 2, so 0.08 molar. Or sorry about that, 0.08 liters, which turns out to be
80 milliliters.
80 milliliters. And if I don't specify, you can just leave it in liters. A lot of times you're going to specify. I don't know. Just said what volume, right? Yeah. A lot of times I'll specify because you know, we don't measure. We don't have any instruments technically that measure in liters here. We usually have things that measure in milliliters. Does anyone recognize anything we've never done before up there? Good answer. So what do? Just pull it all together. Do you agree? Okay. Any questions? I'm not done. We'll go through some more. I know some of you are worried. I will say this though. How many of you feel, yeah, you know what, I get what's going on? There's quite a few of you. Here's the deal. You have 2 sets of problems. I can't remember how many there are. Let's call it 4 to 5 per assignment. Okay? You have 2 assignments. They're essentially due, well, Thursday. What's today? Tuesday. I'm going to pass them out to you here in a second. For some of you are good to go, you're ready to move on. Okay? That's excellent. Go ahead and work. I don't want to slow you down. Some of you would rather walk through 1 or 2 more of these with me. I get that. Please play and do that. Okay? Ultimately, what's going to happen, maybe not today so much, but tomorrow especially, it may happen today, at each lab station are going to be my written out solutions to all of these things. Yeah, I know that they're already on Canvas, by the way. Some of you have already looked at that. Judge checking it out right now. But anyway, those solutions are all on Canvas. You guys can access those anytime you want. Okay? But I'll also have them here, so you guys can see them in a bigger format if you like that. Do a question, check, make sure you got the answer right. Do another one, check, so you got the answer right. That's what we're doing for the next 2 days. 2.5 days, if you think about it. Sound like a plan? Okay. Let me get the, for those of you that want the assignment, actually, I'm just going to pass them all out right now, but I tell you, I will walk through as many more of the remaining 3 ones as you would like to go through. It's really straightforward. These are due Thursday. If you want to start working on them now, you can. If you want to wait for a little bit and go through a couple more with me, that's awesome also. What am I doing? I'm acting like this is a quiz. Which one did you get? Number one. Which one did you get? 2. I'm going to give you 1 also. Here, let me come back. You got 1? I don't know. You guys got 2. Right? You guys got 1. And you guys got 2. And you guys haven't got it. That's finally woke up. Now, Martina, if I happen to see you the rest of the day, you have that sweatshirt on. Take it off. It's on. I don't want to see it.
You can't?
I can see it.
No, you can't. You were going to let me go to the bathroom and turn it over. As long as you can't see Liberty, you're fine.
All right. Here we go. Who would like to walk through another one with me? Okay. Here's the thing. I did this one essentially on my own. I'm going to have this next one, you guys tell me what to do. I don't care who tells me, but somebody else tell me what to do. Nick, pick one. Doesn't matter which one.
Number 2.
All right, we're on number 2. Oh, hey, look at that. They gave us the equations, didn't they? So here we go. FE2. That's why he picked that one, right? Just out of curiosity, is this an acid-base reaction? Is it an acid-base neutralization? Technically, no. There's an acid, but what's not there? A base. Okay, so this is just, a reaction. So, so we get some sulfuric. And a little iron 3 cyanide. Okay, so there's the reaction. Oh, I think this even balanced it. Look at that. 62. Well, that was darn nice of me. Okay. What should I do next? Or first, I guess, would be the good question. Anyone can throw this out there. Yes, Derek. Yeah, I like to write things down above or below to help me focus on the things that I'm trying to do. Do you guys like to do that too? I think it helps me focus on the things I care about. So in this case, we have 31.34 milliliters of this. And 0.534 molar. Over here, I have 21.11 milliliters, and I do not know the concentration. What are the similarities between this question and the first one that we did?
It's like the same except for we're trying to find something.
Yeah, it's incredibly similar, but instead of trying to find the amount of something this time, we're trying to find its concentration. Do you guys agree? This is actually more typical of what you might do in a laboratory setting. So, other than that, it's very straightforward. So what's the first thing I should do then? Anyone?
Find moles of that.
Find the moles of this. Why do I want to find the moles of that?
So you can find.
So I can find the moles of this through stoichiometry, right? So how do we find moles?
Equals mole of volume.
Yeah. Molarity times the volume. So we're looking at 0.534 molar. And what is the volume?
0.0313.
Say this again.
0.0313.
Yep. Okay. And that one's going to be a little bit harder, but 0.015-ish. Because this is, what, a little over half, right? And half of 031 is around 015-ish. Can I have an extra significant figure just for fun? 7.4. Now that's moles of the Fe2 SO4 taken 3 times. As someone had said earlier, to find molarity, I need moles over volume. I currently know the volume, and from here I can find the moles of this, right? Through stoichiometry. So it is a 6 moles of HCN for every 1 mole of Fe2 4.3. So we're essentially multiplying this by 6. Well, some of you recognize 0.016 as a factor of 1/6. So we're looking around 0.1 molar, or 0.1 moles-ish.
1.004.
Say this again?
1.004. Something by 6?
I don't think so. Try it again. Did you put 0.016 in?
Oh, no, I put point.
I got you.
Point 1.
Okay, of HCN. So therefore, all we have to do is come over here and say, okay, 0.1004 moles of HCN. Divide that by the volume, which is 0.02111 liters. So about 1/50th. So multiply that by 50. 0.05-ish.
4.76.
Does anyone remember that did the gas stoichiometry problems, that they all ended up kind of seeming the same over and over again? Guess what you're going to notice? These are all going to...
Does it get harder?
They get different. You know what I'm saying? They get different. Yeah, some of them are going to be a little harder. Oh, let's look at 13. Yes. Yeah. Let's look at 13. Any questions on this one before I continue? Now, 13 is going to be the opportunity to use that new technique that I showed you back with gases. I know it's been a little while. How do you know this? Well, you're given both the volume and concentration of both substances, which means therefore you can find the moles of both substances, therefore it's a limiting reactant problem. Okay, so now, let's start with number 13. What's the first thing we're going to have to do? Jake, please pay attention. No, I'm sure. Are you working? Are you working?
Yes.
But I would like you to pay, are you working on 13? I would like you to pay attention to 13. I know what you're doing. That's awesome, okay? But please pay attention to 13. What's the first thing I'm gonna have to do? You have to write the equation. So what's the formula for aluminum hydroxide?
OH3.
It is. Well, we would say OH taken 3 times. And it is a solution, so we put a Q after it. And what's the formula for nitric acid?
H.
Good.
N.
Keep going.
HNO2.
She's guessing now, isn't she? It says nitric, which since it ends in IC, that means it originally came from something that ended in ATE. So nitrate. And what is the charge on the nitrate ion?
1.
It is, so it's just HNO3. Now, what type of reaction does this appear to be? I'm sorry, what's that? It has hydroxide in it, and it has an acid, so therefore it's an acid-base neutralization. What are the products of an acid-base neutralization? Water and a salt. Which particular salt this time?
Aluminum nitrate.
Aluminum nitrate.
No way.
What's the charge on aluminum?
3.
3 plus. Charge on nitrate, we already determined, is 1 negative. So, is this the right formula?
Yeah. No.
You need to have 3 nitrates to cancel everything out. Balancing. Okay, I got it. Would anyone agree?
Yeah.
Okay. So now we write down what we know. 45 milliliters of this. 0.15 molar. We have 35 milliliters of this. 0.25 molar. The first thing we have to do, oh, and we're looking for mass of aluminum nitrate. So we have a limiting reactant problem because we're given the entire amount of information we need to find moles for each of the reactants. This is, I'm going to show, once again, revisit that new technique that I showed you. You want to use the old technique, we can do that also. I'm going to show you the new technique first. Here's the new technique. Find the moles for each of these. So, moles of aluminum hydroxide is, as we all know by now, molarity times volume. We plug and chug. We take our 0.150 molar, multiply by 0.0250 liters. 15, 3.5, 3.75, 0.0375. Somebody check me on that?
0.00. 0.0375.
Yeah. We're going to do the same exact thing for the nitric acid. Moles equals molarity times volume. In this case, it's 0.25 molar times 35. Whoa, I lied. 0.035 liters. So 1/4, 1/2, 15, 1725, 0.085, 0.085-ish,
0.0875.
0.0008, what's that again? 08 what?
875.
875 moles of nitric. Now, so now we know the moles of both of them. Here's that little trick that I was showing you. Okay? How much nitric acid do I need relative to the amount of aluminum hydroxide? Jake.
How much?
How much nitric do I need relative to the aluminum hydroxide?
It's 3 for everyone.
I need 3 times as much. Is this 3 times as much of this? Can you clearly see that it's not? Because in order to be 3 times this, I would have to be in the 9s with 9 and even above 9. Would you guys agree with that? Okay, so which one's my limiting reactant?
The acid.
The nitric acid. Would you all agree with that? Okay, that's, in my opinion, a pretty easy way to do that. Now, I'll show you the old way too, because some of you prefer that way, and that's fine. Who thinks that they're going to like the old way of doing it? Anyone? Okay, no one. Ashley, since you're so happy today, I'm going to have you pick one of these. I don't care which one. HNO3. So let's say Ashley picks the HNO3. So what she would do, I'm going to put or here. She would take the nitric acid, so she'd go the moles of nitric and say equals molarity times volume. We've already done the work, but this is if you would not have already done the work, okay? So 0.25 molar.
So we don't have to write this.
No, well, if you decide to go the old route, you would have had to have done this, you know what I'm saying? So I'm just showing you what if, okay? And so that gives us 0.00875 moles of nitric, which then we now know is a 1 mole of aluminum hydroxide for every 3 moles of nitric, okay? But then we would have had to have divided that by the volume to get the well, let's just do it this way. We'll just use it as a conversion factor. And we know that there are 0.15 moles per 1 liter of the aluminum hydroxide, which is the same thing as molarity. You guys get where I'm going with that? So that shows us the volume that we're needing. And then, of course, 1,000 milliliters per liter. So anyway, what that all comes out to be is, and I don't have my calculator with me. If anyone did that calculation, that would be awesome and lovely. Oh, that's funny. Oh no, it's not funny at all. Is 19.4 milliliters. So 19.4 milliliters of the aluminum hydroxide required. Do I have 19.4 milliliters?
Yeah.
In fact, I have more than I need. So therefore, which one's limiting? the nitric acid. Do you see what I'm saying? You come to the same conclusion, obviously, okay? It doesn't matter which way you go. However, I'm going to guess that most of you, now that you've seen this, kind of like this. Do you like that? A little bit more than you like this? I get that. I understand that. That's why I like this too. Okay. And now, we're not done with the problem yet, are we? So this was, you can either do this, the limiting reactant piece, either this way or this way, doesn't matter which way. But now that we've found the limiting reactant, what we're going to do is actually answer the question, which is what mass of aluminum nitrate. The other reason I like this is we already know the moles. Isn't that awesome? We already know the moles. So really all we have to do is go 0.00375 moles of aluminum hydroxide, or sorry about that, I lied, 8.75 moles of nitric. And it is a 1 mole of aluminum nitrate for every 3 moles of nitric acid. And what's my next step? Since I'm looking for mass. Yes? I have to find the formula mass of the aluminum nitrate. So whatever that comes out to be. I lost my, I found it. So 26.98 plus 3 times 14 plus 9 times 16. I got 213.01. Ah, 21 divided by 3 is 70. 0.07-ish. .62. There we go. 2 days. How many problems? Is it 8 or 10? I can't remember. Is it 10? What did I tell you, Martina? I said if I see that on you, I'm sending. I don't care. I said if I see that
You
on
don't
you.
see it on me. Yes, someone that walks through the grass that sits.